Hello everybody. Today I'll talk about chapter 7, which about some bipolar junction transistor, small signal amplifier. So we'll study some amplifier circuits with AC and DC. So this chapter is focusing on analysis of a small signal amplifier. So we do not really consider the compliance and stuff. We do not study it because we have a small signals. So we'll not be concerned about the compliance or maximum load power, the dissipation and distortion, all this stuff. The small signals are the ones that one producing output signals that are well below the clipping limit. So as I said, you do not care about the compliance here. There are two ways to analyze the signals. One of them is called H parameters. One is other method is called R parameters. Usually, when you have any amplifier, you can model it in different ways. Like H parameters, this is hybrid parameters. We call it hybrid because usually there is each H. Usually, you have 4 H's, for example, or 4 parameters. Each one will have a different relation. One is voltage to current, one is current to voltage, one is voltage to voltage, one is current to current. So they are different. Sometimes when you study, for example, network like two-port networks, for example, sometimes you use Z parameters. We call them Z parameters because they are all voltage to current ratio. So, for example, V output over V input, or V input over V output over I output, or V input over I input, V output over I input, and so on. They are all V to I ratios. That's what we call them Z parameters. But hybrid is different. Also, what we will use in this chapter is R parameters. So for any PGT, we can simply model it in like this. This is the AC model. So we have this current source, which is normal. This is IC equal IB time beta. The only difference here from the previous chapter that we use a small letter because this is AC. So the relation here is the same. This R prime E, okay, this is the relation between VBE, the voltage PE, to DIC, the current here. So the current, okay, is this part, the voltage to the current. Okay, so we get this one from this formula, which is very similar to the current in the diode. If you remember the current in the diode, it has a very similar relation to this, where IS is the saturation, the reverse saturation current, and VBE, this is usually 0.7 volt, as I mentioned before, but here we just have it as variable, okay, because it is a function here. We need dVBE by DIC. So we have this as a variable. Q is a charge of electron, we know this. And N, this is the number quality factor that is usually between 1 and 2. And K is the Boltzmann constant, this is the constant, and T is the temperature. Okay, and usually if we have, for example, 300 Kelvin is the temperature, this Q divided by KT, is around 38.6. Okay, so if N is 1, for example, so this will be VBE time 38.6. Okay, 38 time almost 40 VBE, 40 VBE, yes. So e to the power of 40 VBE is a very large number. So you can neglect this one here. You can neglect the negative one. So in this case, you can just take this one here. IC equal 38.16 VBE. That's it. Okay. And then you can differentiate IC with respect to VBE. DIC with respect to VBE, you differentiate this one here. IS is just constant. You take this outside, 38.6 outside. And you repeat e to the power of 38.6 VBE again. Okay. Then when you compare this one here, this result What is this result? This result actually is this part here is here. So it is actually 38.6 times IC. So you now the differentiation IC by DPE equals this here. But we need to have the opposite, VBI by DIC. Then we have to flip this. When you flip this one, we'll flip this one also, like this. Okay? So now dVBE by DIC equal what? Equal 1 over this. 1 over this. Okay? Then you can change this one to 1000 and make this answer is in millivolt. Okay, so this is the answer. 1000 over 38.6 will be in millivolt, 25.9 millivolt. Or we can simply say this is 26. So this will be RE prime. RE prime. So RE prime equal what? Equals 66 millivolt over IC. Then usually if you want to calculate this RE prime, how do you do that? Remember how we calculated IC in the previous chapters? We do the same. Usually we use the input loop. You look at the input loop to find the voltage or to apply Kirchhoff voltage law in the input loop to calculate IC. And from this IC you can calculate RE prime. So this is what we will do in this chapter. Okay. There are different configurations for the amplifier, transistor amplifier. Like for example, we have a common emitter, common collector, common base. For a common emitter, for example, the input is at the base, the output is at the collector, and this one can give you amplification in voltage and in current. So it has AV and AI. So AV is number, big number. And the same AI also is a big number, but it will give you a phase inversion. This means that you have a negative sign at the output. Okay, so this is similar to the inverting amplifier, for example. For the common collector, if you have the input at the base and the output as the emitter, you will not have amplification in the voltage. In the voltage, the input voltage and output voltages are basically the same. Even maybe the output is a little bit less. So for example, the input is 10, the output is 9.8, for example. So they are close to each other. But we provide here, it will provide current amplification. And it will maintain the phase. There is no phase shift. So in the output and input are in phase. There's no negative sign. Okay, and this is called emitter follower. This one is a different one also. It provides voltage, but it doesn't provide current amplification and also maintains the phase. We will talk about this too in this chapter. The first one look like this. So here you see the input signal is at the input, at the base. The output signal is here, across this collector, to this resistor. And we have a capacitor as the output and a capacitor as the input to suppress or to block the DC. And usually when you want to solve this problem like this, we have to use a superposition rule. Superposition that you calculate the DC solution and AC solution. Solution when you have DC only, and solution when you don't have DC, you just have AC. Okay, so this is the solution. So again, C in and C out are used to block the DC. Okay, they are chosen so that the reactance is very small with respect to the resistance. For example, Cn and close to Rp. So the reactance here is very small. What's the reactance for capacitor? Is 1 over J omega C. So this one is very small with respect to this one, and this one is very small with respect to this one. Here we have also CE also. This is for the emitter. Okay, and we have a resistor here. If you look at the emitter side here, we have two resistors. They designed it so that we have two resistors. One is called RSCW or swamping resistor, and this is a regular emitter resistor. The swamping resistor is useful because we can use it to control the voltage gain. Okay, so of course, the higher the highest voltage, the highest gain is when we have RSW equals 0. If this one is 0, you will get the highest voltage gain, AV. Okay, but sometimes you need to control it. You don't need to have, for example, 100 amplification. You need amplification to be limited. You want to control it. Okay, so RSW, if RSW is 0, you will get the highest amplification. Let's say 100, for example. But if you want to get it down to 10, for example, from 100, then in this case you have to add this resistor. Okay, in case of DC, usually we have these capacitors are open circuits, open. So for example, here the resistance of the emitter here equal what? Equal this one plus this one, because this one is open. The capacitor is open in case of DC. So the resistance here is these two together, series. But when you are studying the AC will make the capacitor will be short, because as I said, it is very small with respect to the resistor. And also in high frequency, it is usually very small. Okay, so now if this is short circuit, this will short this resistor. Okay, which makes the emitter resistor what equal what RSW. Okay, if this one is short, for example, here. Okay, let's see. We'll see this later on. This one could be an AC will be short, and so on. Okay, so let us see how we solve it. So we'll solve it, as I mentioned before, using DC and AC. So in DC, we do it like in the previous chapter. AC, we will do it this chapter. So in this chapter, we calculate IC. When we calculate IC to calculate RE prime, we use the DC solution. So here, assume that you have this circuit here. This is a circuit, and you wanna analyze it or calculate the gain, calculate the impedance, input impedance, output impedance, and so on. These are the three main parameters for any amplifier, as I mentioned in chapter 6. Then in this case, you need to replace it by this model here. This one here is what this is the AC model. In the AC model, you do not have a DC at all. In the AC model, you don't have a DC. So let us see what happened here. What happened is that you don't have a DC. Okay, so where is this V, negative VE? Okay, it's ground. Is it ground? Yes, it is ground. Why? Because in AC, when you use superposition, you remove the source. Then the source is shorted. It's ground. So this is connected to the ground. And this CE, the capacitor, will short this resistor. Then this RE here, okay, will be this capital RE. Will be capital RSW. Will not be this one. You cancel this one. So the resistance here will be this RE. Okay, so this is RE equal what? RSW. Again, here this is a ground. The capacitor is short circuit in AC. Then they will cancel RE. Then the total resistance from here to here is what? Is just this part, which is here, this one. Okay, from E to the ground, you have this a little RE equal what? RSW, because this one is shorted. Okay, what about this one here, RC? What's RC? The VCC is grounded. When it is grounded, this means that it is connected to the ground here, and this is short. Okay, so in this case, this will make RL and RC parallel to each other. Is it? Right. Okay. Why? Because VCC is a ground. VCC is ground. Okay. So now RL and RC are connected to the same two nodes. This one and the ground. Then in this case, this will be equivalent to RC. This little RC. So RC equal what? RC parallel with RL. Okay. What about this one here? RP. This little RP is the same like this one. There's no difference here. This one and this one are the same. This one will be capacitor. This capacitor will be short circuit. So this is the AC model that we will solve. Okay. So the first step here is to know what is this parameters RE, little RP, little RC with respect to the real resistors. This real resistor is a capital. Then after that you calculate IC. IC. How do you calculate IC? IC equal what? IC from this one here equal what? Equal here, for example, you know, if you know the voltage for somewhere, you use this loop, for example, to calculate the voltage, for example, to apply here, for example, here, this point, to calculate IC. How do you calculate IC? So if this one is negative VEE, this one will be positive VEE. So this voltage between this point and this point will be what? Will be the voltage here, across this one, plus this voltage, which is 0.7 volt, plus IC times this. That's how we do it. Usually, this is how we do it. And then from that, you calculate RE.